Okay, so this is lecture 6, part 2. So in the first part, we did all of our area between two curves in terms of x's. But you can also find regions determined by graphs that are x equals a function of y. Okay, so we're going to find the area of the region enclosed by the curves x equals 2y squared and x equals 4 plus y squared. So first, let's sketch the curve. To sketch the curve x equals f of y, first we sketch the curve y equals f of x, and then you reflect your sketch about the line y equals x. So essentially, you flip your x's and y's. So really, you can think about turning your paper and sketching it. So if x equals 2y squared, then I'm thinking about drawing y equals 2x squared, but sideways, if you will. So the so this would be a parabola that is centered at 0, or its vertex is at 0, 0, and it opens up. So instead of opening up, it's going to open to the left, to the right, where the y's are positive. So it's going to go like this. And then you have x equals 4 plus y squared. So if I go to 1, 2, 3, 4, then I want... this is a parabola that also opens to the right. So it's going to look like this, I think. And so what happens is we get this space between the two curves. And again, if I'm not sure, let's see if I did it right. Let's go to Wolfram Alpha and check. So this time we're going to plot x equals 2y squared. And x equals 4 plus y squared. And I'm going to get rid of the bounds. So those are my two functions, and let's see what happens. Okay, so what they did was they flipped the x's and y's for me. But that's not what I wanted, right? I wanted in terms of x and y. And so if you flip that, if you flip your x's and y's around, you get exactly the same thing, but on to the right side where y's are where x's are positive, which is exactly what I showed you, right? So that's exactly what we got here, right? If we turn it, if we were to rotate it and reflect it around the line y equals x, which of course is like right here, we would just kind of flip it about that line and it would give us what was vertical, what we just saw. Okay, so that's what that means. I don't always think about graphing it and then flipping it. I kind of think about what does this look like if I switch the x's and y's, and then think about that on its side kind of thing. Okay, so all you're doing is thinking about it on as your y, as the x-axis as your y-axis and the y-axis as your x-axis. Okay, so the first thing we need to know is what, so I'm going to think about, instead of thinking up and down like I did last time, I'm going to be thinking left and right. So this direction, right? And so my top function here is this one. And my bottom function is this one, if I'm looking at it right to left. So then what we really need to know is how our y values change. So I need to know what are these points here where my graphs intersect. And so we do that the exactly same way we did before. So you're going to set 2y squared equal to 4 plus y squared and solve. So I'm going to subtract a y squared from both sides. And that's going to give me y squared equals 4. Take the square root of both sides, and that gives you y equals plus or minus 2. So this is positive 2 and negative 2. Okay, so all we're going to do this time is do exactly the same thing, only now instead of integrating with respect to x, we're going to integrate with respect to y. So we're going to take the area is going to be the integral from negative 2 to 2. So now they're y values. So I'm going to get a dy over here. And I want the top or the right function, so the purple one here, which is the 4 plus y squared, minus the blue function, or the function that's at the left, and that's my 2y squared. And then your dy. And notice how everything's in terms of y's. So I get a nice integral here. So the integral from -2 to 2, I can take 4 minus y squared when I simplify that. And we get 4y minus 1/3 y cubed from -2 to 2. And then we plug in our 2, which gives us 8 minus 8/3. Minus, when we plug in our -2, which is -8, minus -8/3. And I can distribute this negative. So that just means I get 16 minus 16/3, which if I calculate, turns out to be 10.6 repeating. Okay, next, example 5. Find the area of the region bounded by these two curves, y equals 1 over x and y equals x. And, 3 curves, y equals 1 over x, y equals x, and y equals 1/4 x, assuming that x is greater than 0. Okay, so that means right off the bat that we're only graphing them on the right side here. So 1 over x looks something like this, and let me do it in color. So purple function. Y equals x is this one. And 1/4 x is going to be, that's a slope of 1/4. So if we start at 0, I'm going up 1, right 4. So it's going to go more like this. Okay. Okay, so when I think about this, if I cut it, if I think about drawing a vertical line here, it's because my area, let me shape my area first. So this is what I'm looking for, is this little triangle kind of shape right here. And notice that the bottom function is always the same. So the red one on the bottom is always the same. But right here, the top function changes. To the left, it's the blue one. To the right, it's the purple one. So I've got to figure out what is this point and what is this point, okay? And of course, we're starting from 0. So in order to find the first point there, it's where the purple and the blue line connect. So purple was the 1 over x, blue was y equals x, and red was y equals 1/4 x. So in order to find the first black dot, I need blue and purple to be equal. So I need when 1 over x is equal to x. Multiply both sides by x, and that gives me 1 equals x squared. Take the square root. That happens at x equals positive and -1. Of course, I'm with x greater than 0, so this means that this is at 1. The second point here is where the purple and red correspond. And so that's when 1 over x equals 1/4 x. And so if we multiply everything by 4x, we get 4 equals x squared. Take the square root, and x equals plus or minus 2. Again, x is positive, so this is when x equals 2. So that works out really nicely for us. So now I'm going to think about cutting this into 2 pieces, because again, on the left of my black line, the top function is blue, and on the right of my black line, the top function is purple. So I'm going to set up 2 separate integrals. I'm going to set up the integral from 0 to 1, and the integral from 0 to 1 has the blue function up top, which is x, so that comes first, minus the bottom function is the red one. And the red one is the 1/4 x dx. Plus the second integral goes from 1 to 2 because that's the interval that I'm on. The top function is the purple one, so that is 1 over x minus the red one, which is 1/4 x. And we get dx. So now we just have to solve these 2 integrals, and that'll give us the area between the curves. On the one on the left, I can combine those and get 3/4 x dx. That's 3/8 x squared dx. Sorry, not dx. And I'll show that to you. That's 3/4 times 1/2 x squared, evaluated from 0 to 1. And that's going to be 3/8 x squared evaluated from 0 to 1. When you plug in 1, you get 3/8. And when you plug in 0, you get nothing. So far I have 3/8 from the one on the right. The one on the left, I get the natural log of x minus 1/8 x squared evaluated from 1 to 2. So when you plug in the 2, that gives you the natural log of 2. Minus 2 squared is 4. 4 over 8 is 1/2. Minus when you plug in 1. Well, the natural log of 1 is just 0. Minus plug in 1, you get 1/8. So this is the natural log of 2 minus 1/2, and distribute your negative, plus 1/8. So this is the natural log of 2. And I'll bring it down here in line with this. So plus the natural log of 2. And let's see, that's negative 4/2 plus 1/2 is minus 3/8, which just turns out to be the natural log of 2. And that's my area between the two curves.